So we left off talking about finding the minimum element in a BST, and we said all we're going to do is keep on going left until we've reached the very end of the tree and its left children, and this will be our minimum. So this is exactly what this algorithm is doing. And this is just to handle the case where we are past a tree that's null. It's an empty tree, so we're just going to return null. But any other tree should have a minimum. The maximum would be the exact same thing, except you're going to be looking at the right children and going to the right subtree every time until you reach the very end, the very last leaf. Also, actually, I just made a mistake here. The minimum and maximum don't necessarily have to be leaves. So, as an example, if you look at this node and you were looking for the minimum, and you had something like that, and this would be a leaf node. Well, when you get to this point, you realize that this is null. There's nothing to the left. So this will be your minimum. And it's also an internal node, so not necessarily a leaf node. And similarly, if you're looking at the maximum, you're going to be going to the right. And suppose at one point you had something like that. At this point, you know that there's nothing to your right. So this is your minimum, but it's not a leaf node. So it doesn't necessarily have to be a leaf node, the minimum and the maximum. Adding an element to a tree. So adding a key to a root. One point worth noting is that we're always going to be adding a leaf. So whenever you add an internal node, it's always going to be this algorithm adds as a leaf. And in fact, when you add anything to a binary search tree, it's going to be a leaf to the very end. So what you're going to be doing is going through your tree, and once you reach a null position, then you could replace that null by the key that you have. So first, if your tree is empty, it's directly going to go to this condition. It's going to come out to be true, and so you're going to create a new key. So we're creating a new BSD node and returning it, and we're going to be assigning it to root and returning root. So this is if it's empty. If it's not empty, then we're just going to make these comparisons. Is the key less than the root? If it's less than, then we're just going to call that same function, the add, once more, but on the left subtree, or on the left child. And we're going to keep on doing this until we reach the very end. If the key is larger than the root, then we're going to do the same thing, but to the right subtree. So we're trying to find the right position where to add our key. And if it turns out that none of these actually match, then the key could already be present. So we're just going to return that key. We can't have duplicates of the same key. Remember that. So we're going to keep on doing this until we reach our base case where we find a root or a node that's null, and we could just put our key there, and it's going to be in its proper position since we've been through these conditions. The remove is actually a pretty long algorithm, and we're going to look at it in a next video. So right now we're going to skip that, and we're just going to go to the very end here, and we're going to look at the similarities and differences between a binary search tree and a binary search that we looked at before. Sorry, that moved. Yeah, the screen just moved. So we're going to be looking at the difference between binary search tree and binary search. Binary search, if you remember, was applied on an array whose elements were sorted. And we took advantage of that, and so what we did, we were looking for a particular element, we just compared our element to the one in the middle, and if our element was less, then we discarded everything to the right, and you just kept on going, doing the same thing with the elements that are remaining. So this actually reduced the time we spent searching for an element. So let's look at the differences and similarities. BST uses a tree, binary search uses an array. The BST, what is good about it is that once you find an element, it will stop at that element. It will not carry on. Whereas in a BS, if you remember in our binary search, if you remember our algorithm, what it did is that it went through, and even if we had found our element, once you make a comparison and the key turns out to be the same as this one, we kept on splitting our array into halves until we had one last element and we had our low pointer equal to the high pointer. So this actually creates a little bit of wastage, so you keep on doing the same algorithm over and over again, whereas in this case you actually stop, and we're going to see how this happens. And in the case of a binary search tree, there's no reduction guarantees. If it's a one long branch tree, then you're just going to keep on looking for your element, going